Okay. From here, I would say it's going to get a little bit easier on you to understand these topics because it's kind of, we are going back to chapter 3, discussing about electronic configurations. The only difference is, in this case, we are discussing about electronic configuration of the ions. Not just electronic configuration of elements, but electronic configuration of the ions. So electronic configuration of the ions, you can predict by knowing how to calculate the number of electrons remained on the element. Let's see if we can come up with a formula. Yes. Let's say P is number of protons. E is number of electrons. Okay. You can predict how many number of electrons remained if you use this formula of P plus E is equal to charge. Let's see. How do we predict that? Is if someone says calculate the number of electrons remained in Na plus, right? The example that we are going to discuss at the bottom of the page. So you know that there is a charge of +1. So P is number of protons. We know that sodium has 11 protons, and there are, we don't know how many electrons in it. That's what you were asked to identify. So electrons. So charge is +1. So to find electrons, you will say 11 minus 1, there should be 10 electrons. I think I should rearrange this equation to E is number of electrons is equal to P minus charge. Okay. If someone says, for example, calculate the how many electrons present in Cl minus, then you can use this formula of E is equal to P minus charge, which is, it is having, which means it currently had 17 protons and it currently had a -1 charge, which is equal to 18. That is how you would identify how many electrons left in an charged species. So basically, once you find how many electrons are there for a charged species, predicting the electronic configuration is very similar to how you typically do. So for sodium, instead of writing electronic configuration for 11 electrons like this here, if you know that it is going to have +1 charge like this, you would only write electronic configuration for just 10 electrons instead of writing for 11 electrons. So for chlorine, instead of writing electronic configuration for 17 electrons, you would just write electronic configuration for 18 electrons. And you would say, if at all it matches with any noble gas element, you start using this word. We're going to specifically discuss again later, but you can start using this word from here, isoelectronic. You would use that word isoelectronic whenever more than one species is going to share the same electronic configuration. We know that neutral neon is going to have the electronic configuration of 1s2 2s2 2p6. If Na plus is also going to have the electronic configuration of 1s2 2s2 2p6, you can say that they have isoelectronic configurations one with each other. Here is a list that shows the elements with isoelectronic configuration. In general, if they were in the same period, it is a little bit easier to predict. All of these have isoelectronic configuration with each other, with its noble gas, neon, and all of these are in isoelectronic configuration with argon. These two are in isoelectronic configuration with the krypton, and these two are in isoelectronic configuration with xenon. And lithium is in isoelectronic configuration with helium, and sodium and magnesium too is in isoelectronic configuration with the neon. K plus and Ca plus 2 is an isoelectronic configuration with argon. Rubidium and strontium is an isoelectronic configuration with krypton. And cesium and barium are an isoelectronic configuration with xenon. And in the transition metals, they were a little bit complicated, and I do not really want you to worry about them, and it just making things more complicated. When it comes to test any one of those topics on you, I would let you know what you should know about those transition metals. Otherwise, I just want you to focus on main group elements of 1A to 7A. Okay, here the question is asking, write electronic configurations for the following ions of main group elements. So without watching this video further, by taking a pause, I want you to answer it. First of all, I want you to use that formula. I like that formula. It says charge is equal to P, sorry, I just proposed that formula and I forgot it. No, it is E is equal to P minus charge, right? So I want you to first find number of electrons present in each one of these charge species. N3 minus. So to predict number of electrons here, we know that nitrogen has 7 protons and the charge is -3, so which should be total 10. And Ba plus 2, and we need to find how many protons in it. It's a large element. And the beryllium, you need to find how many protons in it, and it's a large element. You can do that. Once you find that, you can write the electronic configuration for that element. Most of the times they were equal to particular noble gases. So barium electronic configuration, after it lost 2 electrons, it is equal to krypton, and beryllium, its noble gas electronic configuration is equal to helium. Okay. Typically, this is what you have to do when you write the electronic configuration of ions. Most of the times they end with electronic configuration of noble gases, so it's not too unpredictable. But in order to correctly write those, you need to correctly count number of electrons a ion is going to have once it forms the charges of negative or positive. So here a few other examples of if, well, one of the common confusion students have is if you have electronic configuration of d orbitals, which electrons to remove once it forms the ionic charges. It's not a trouble to write the electronic configuration of a neutral element. You would use that flow chart that we discussed, like 1s, 2s, 2p, then 3s. You would use that flow chart to fill the electrons. But if we talk about either adding electrons is still not a problem. You know how to follow that flow chart. But if you talk about removing an electrons, I've seen some students having this confusion of where to remove the electrons from, right? You always remove the electrons from the outermost shell. No matter how your electronic configuration ends with, you always remove it from outermost shell, right? So which means the classic example is iron. Iron, if it loses, for example, 2 electrons, where is it going to lose those electrons from? There is shell 4 and shell 3. It has to lose from the outermost shell, which means it has to lose entire 2 electrons from shell 4 if it is going to lose only 2 electrons. And if it has to lose more than 2 electrons, then it would first lose 2 electrons from the outermost shell. Then it would lose whatever the remaining electrons from the remaining lower shell orbitals. So in this case, it is turning into 3d5 by losing 3 electrons. In the first case, it is turning into 3d6. Pay attention that here it is not losing any electrons from 3d. It should not, because 3d is not the outermost shell. But again, I know when we fill the electrons, we fill it in 4s first. So we can make the reasoning like, why not we take it out first? Because why we are taking it out first? Because we are filling it first. Even though we fill it first, when you write the electronic configuration, we have to remove the electrons from the outer shell first, because it is much more easier to remove electrons from outer shell first. But adding an electron is a different story. Okay, that's why it's a different story. So pay attention that you always need to remove the electrons from outer shell orbital no matter whether you have d orbitals or not. All right. so it is asking you to write the electronic configurations of these elements of Zn plus 2, Mn plus 2, Cr3 plus. I want you to use that formula of E is equal to P minus charge and predict how many electrons remained and write the neutral electronic configuration of all of these metals, especially for transition metals like zinc, manganese, and chromium. First, write the neutral element electronic configuration, then find how many electrons left using this formula of E is equal to P minus charge, then remove the outermost electrons first, okay? So once you do that, your electronic configuration should be equal to argon 3d10 for zinc because it is only losing 2 electrons, so which means it lost its 4s2 electrons, zinc, and Mn plus 2 lost its 4s2 electrons, and chromium plus 3 lost its 4s2 and 1 electron from 3D. Okay. From here, what we are going to talk about is general regions of the periodic table,